Hello, I'm Ben McClelland from Versity. I'll be co-presenting with Gary Greider from Lanel here, talking about our new project that we started about 5 months ago, an S3 Gateway, primarily to support the ingest workloads for our new storage platform. So to kick off the talk, Gary's going to give some examples of how they're using this.
Thanks, Ben. So my apologies for those that sat through my talk last night. This is going to be a little bit overlapped, but I'll try to cover it at a high level in case you weren't there. So we have this use case for computational storage that I talked about last night, and it's essentially our grid-based codes, which is our large simulation codes, the largest ones, and they think of themselves as columnar, so it's really a distributed set of arrays across millions of cores of memory, and each one of those, the application really thinks of those as a distributed array, which is essentially a column. And when they write data out, they've always written columnar, even before it was called columnar. And so we have a lot of columnar-oriented data, and we produce a lot. The typical size of the simulation output per time step is about a petabyte, so it's pretty large. And with 100 columns, even one column is still pretty large. It's all floating point, 64-bit floating point. And so we were looking for a way to do analytics on those very, very large data sets, because it's not just one of them. You have one of those every time step. So if you did 1,000 time steps, you'd have an exabyte. And so one of the things you want to do naturally when you have that much data is, when you're trying to do analysis on it, is you want to throw as much of it away as you're not interested in. And we've been looking for good ways to do that. And since it's all columnar, using the Apache ecosystem for indexing it so that you can quickly do analytics and not read as much as read as little as possible and just get what you're looking for. And there's a huge Apache ecosystem out there with lots and lots of tools. Presto is one example. Iceberg is another. These database connectors, ADBC, came from that universe. And so anyway, that's the goal. And so the idea is, instead of writing out our custom columnar format, we would write out Parquet chunks. And of course, it's going to be a lot of them, because you don't want to have one great big petabyte-sized Parquet chunk. You'd have lots and lots of little ones, and then be able to use those tools to do analytics on it for reducing the data, so that when you read it up, you don't have to read the whole thing. And this is sort of a poster child for computational storage, because we want to get reduction as close to the storage as possible, so that we're not moving petabytes, we're moving terabytes, which would be great. And so that's why we're calling it a computational storage, project. It's object-based. Why is it object-based? Because if you're going to push down some piece of the reduction part of the analytic as far down close to the device as possible, the device needs to understand what's there. It can't just be blocks. It has to understand this object that made up of these blocks is a Parquet row group. And so so it's hard to do that with block. You can do that with object. You can do that with file. We chose object because we thought file was probably a pretty heavyweight thing to do at the device. It's not impossible, but hard. And so anyway, we said, okay, fine, let's write out a whole bunch of objects and push them down to object storage devices, and then teach the device how to do simple queries for reduction. We started this project, and we were looking around for an object gateway, an object server to use to write our data out, but it couldn't be an object system, because we were going to put object storage underneath it, prototype object computational storage underneath it. And so we needed sort of a shim, a gateway type product for writing the objects from the applications out to these object computational storage devices, which were on NVMe. And there wasn't such a thing exactly. There was, MinIO had a gateway for years. It was open source. A lot of people used it. Maybe people in this room have used it. But it was deprecated for whatever reason. So we went to Versity, and they had a need for an object gateway for them because they have an HSM product that they have customers that want to view that not just as files but also as objects. And we helped them a little bit, and they helped us a lot by building a really first-class object server that has a plug-in back-end. So you can sort of think of it as a fuse layer, but for object. So it has all the S3-isms up, up to the app, and then downward, each one of the put, and the get, and the select, and the delete, and all those things are plugins that you can do whatever you want down there. And they put their special backend in it, which is very POSIX-y, and for this, it's not POSIX-y at all. It's very object-y, but it's mapping from a TCP object into an NVMe object, more or less. And so anyway, that's the reason that I'm up here, is to talk about one potential use case for this new gateway. It's a Go-based gateway, which he'll tell you about, but it seems very performant, at least so far, and quite well done, actually. So if you have need for using it, talk to Versity about using it. It's open source, so that's pretty neat. So anyway, that's the concept. The query side is basically trying to just use the Apache ecosystem for that. So an app would do, use ODBC or whatever to, open up a conversation with something like Presto, and Presto would farm out a lot of tasks to do the erasure, and we would push the erasure down as far as possible. Not the erasure, the query. We would push the query down as far possible as we could, and we use Substrate for that. So Substrate takes SQL statements, breaks them up into graphs, a graph, and you can decide which pieces to give to what function to give to the OCS. So push down as much of it as possible to the OCS. If you can't do it all, do that at a higher level. If you can't do it all, do it at a higher level yet. So the idea is you push down as much as possible, and it sort of follows the principle of if the bottom layer doesn't work, you can always do it for the higher layer. So if if the OCS breaks, instead of pushing the select to it, you just do a get, and you can do it at a higher level. So anyway, that's the idea, but that's not the point of this talk. The point of this talk is about this open source gateway product, and that's one of the reasons why we were interested in doing it. We have another reason that we were interested in an object gateway, and that is we have this system that we wrote a decade ago, roughly, for what we call warm tier, sort of our warm tier. It's disk-based. I don't know. It's a few hundred petabytes, and it's highly parallel. And it's interesting. It's really kind of a file system, but it's immutable. So the objects, the files are immutable, and it's a file system because all of our security at the laboratory for the last 30 years or more has been based on POSIX. It was very difficult for us to move to an object model. We looked at a lot of object storage servers, and we didn't like what we saw, at least back then. You spent an awful lot of time in TCP, which we don't spend any time in TCP with this thing. And we also, at the time, were struggling with failure and failure domains. And we find ourselves in a little bit of a unique position in that we have little files and big files, and while everybody has that, our big files are a petabyte and our little files are a byte. And that's at least 3 orders of magnitude more than probably the typical. And so if you have a petabyte sized file, you have to stripe it across a really, really large number of things to get to get it ever put out there, right? To move the data that fast. And And we also have this really bad thing about losing bytes, right? If you lose any one byte of that petabyte, the entire petabyte is useless and you might as well throw it away, which doesn't really happen very often, right? You think about objects in the cloud, they might be a picture, and it might be a megabyte you lose or something. It might be a movie and you might lose a gigabyte or two, but six orders of magnitude bigger, that's where we live. And so it's kind of an odd, failure domain kind of a problem. And we see two kinds of failures. We see failures that are random incidence rate, bathtub curve kinds of things, and we use normal erasure for that. But we also have these things we call correlated failures, which are things like this row got too cold for too long and caused higher failure rates in that row. Or, we had this workload that did a really different thing, and it did it to 10,000 disk drives over and over and over again, and it caused the grease to build up in one particular part of it. I mean, these sorts of things happen when you do the kinds of things we do, right? And so we had one day where we lost between 400 and 500 drives, which isn't very many across the whole thing, but that's a kind of thing that system admins cringe, right? They don't want to go to work that day. And so we were looking for an erasure scheme that, this was a long time ago, that would deal with both kinds of failures. And so we use this two-tier failure or erasure system where there's a top tier of erasure, big chunk, 100 megabytes or something from Luster is read into memory. Of course, in parallel, lots and lots of machines doing this. They break that up into 10 megabyte chunks. They use ISA-L and AVX in Intel to create two more erasure chunks. So you have 12 10 megabyte size chunks. Each one of those chunks gets sent to a ZFS server, and the ZFS server writes those things out as files, and the files are erasured by ZFS and have all the normal ZFS recovery and stuff in them. And so the bottom tier is normal ZFS and really deals really well with these random incidence rates. But if you have one of these really bad days, you can use the top level erasure to recover. And it's not just like I lost a rack. Again, it's usually way more sinister than that. It's usually a particular batch used a particular way for too long, and they start failing at some incredible rate. And it's hard to keep up with that, right? And so it can be just lost a rack, and that's easy. And if you ask the sysadmins why they like this, it's because they never have to come in at night. They lost a rack, who cares, right? But if you think about it over the longer term, there's these sinister things that happen, and they do happen at big sites. And anyway, so we built this system, and it has a file system-like interface, although it's immutable. But we have people that want to pull the data from object, right? They want to see the files as objects, and so we needed a gateway product to, let them have they want to download a Python thing off the internet and just run it and have it just work, right? And we needed an object server gateway system to put in front of this thing to front the data. And so anyway, that's another use case. And I imagine there's lots of use cases out there that people have for this. But so those two things were our motivations for working with Versity, and we thank them very much for working with us. Next, Ben.
Gary, that's all public on GitHub, right?
It is.
Versity Gateway.
It is.
All right, thank you, Gary. Yeah, so this is going to continue now with just kind of the overview of what the gateway specifically looks like, what we're developing there, and some collaboration that we've worked with on the way. There's going to be some one customer use case as well for in production deployment. A little bit about Versity, just so that you can understand how we're using the gateway, is that we ship software that manages large-scale archive systems. The underlying file system is an open-source distributed file system, and then we have some proprietary archive manager that runs on top of our file system that manages all of the archive tiers. Global install base, under management, about 2 exabytes of data, 80 sites, just so that kind of give confidence that we're here for the long term. And we also have a real product that's generating revenue, so the gateway isn't our primary product. This isn't something that we're going to be changing licensing on or try to start charging people or flip the script here at any point. This is meant to be an enablement for the gateway, for the community, and it's not something that we're depending the company on or anything for any kind of revenue here. We needed the capability to ingest S3 workloads into our storage systems, so just like Gary was mentioning, into his storage systems. We had the same kind of demand from our customers, is that we have a POSIX file system, but they have these new apps that only speak S3 or have workflows that were more S3 centric, and so we wanted to put the S3 connector on top of the system that we've already deployed. We looked around, didn't really see any other viable projects out there. So Gary mentioned the MinIO project. That was something that we had been using for a while. But then once the gateway portion of that was deprecated, there wasn't really any other viable options out in the community. Or there was maybe some others that had a bit too much complexity. We're looking for the simplified model, very similar to what MinIO did with the single command, easy to run, easy to set up, not really anything to configure, so that was really the target that we were looking for. This is a ground up rewrite from scratch, so we're not taking anything. We took concepts from other gateways out there, but all of this code is written from scratch. It's all our copyright, and so we don't have any licensing conflicts within the repository here. The goal of this was obviously the interoperability with current S3 clients out there. We're not trying to support the entire S3 protocol. It's just enough for enabling the clients that we need, but it's also extensible. So I'll show a little bit later that we can add more to the APIs as needed here. But the initial effort here is mostly just like the CRUD operations. So we're just trying to do the puts and gets and multi-part uploads and stuff. That's our main focus. We're a Go shop, so all of our user space stuff is written in Go, so that was kind of where our expertise was anyway. It kind of worked out that it has the performance and the frameworks that we needed in order to implement the project. So that kind of worked out well for us here, but that is the whole project is written in Go. We did need it to be modular because we wanted some community adoption and collaborations on this, and so we didn't want this to be custom to our software system. We wanted to enable other back-end platforms, so this is where the collaboration with Los Alamos and some of our other partners comes into play. So this was designed from the start to be very modular back-end, and there's other components here that you'll see kind of modularity throughout the project here. We also need it to be scalable. We need to be able to load balance across multiple of these. Our system is a distributed system, so it's not going to be sufficient to have like a single gateway fronting all of the S3 traffic. We need to be able to have multiple gateways across multiple systems and be able to load balance across that. That's our typical customer deployments. We needed this to be open source just to foster the collaboration. So this is all Apache 2 licensed code here. The initial collaborations involve Los Alamos and POSI Supercomputing Center. They're one of our other customers that heavily utilizes the S3 gateway in a highly distributed fashion. So the gateway is a stateless gateway that goes into the storage systems, and so that allows us to satisfy the scalability requirements that we had. So we can have any number of these gateways fronting a storage system. All of the consistency and caching and everything is up to the back-end storage systems that are there. So there's no complexity within the gateway that requires clustering or synchronization or anything. They're stateless, so you just run as many of these gateways as you want on top of the storage systems, and you can load balance across them because each request is independent on itself. The main thing here is like multi-part uploads. You might want to spread a whole bunch of part uploads across a lot of gateways, so you get the parallel aggregate performance of the cluster. So the Versity platform has a POSIX file system in it, and then the archive manager that writes out to object or tape or cloud. It kind of manages all the copies there. So we ingest data into the system and then assign policy based on administrative rules in the system. And then those rules tell us like what copies do we make in what archive tiers. Because it's a POSIX, it's an in-kernel POSIX file system, we've got a pretty awesome kernel team, and that file system is also open source, so you can find that on our GitHub page as well.
Is it upstream in the kernel?
It's not upstream. We have a next generation that's coming. This one's not quite appropriate for upstream, but we're working on a next generation one that is going to be upstream. Most likely that will be. And we have the kernel team that actually can support this. So we have some developers that are very involved in the community here. So we do have both the code and the team that's capable of doing the upstreaming. So yeah, very interested in collaborations and community involvement here with multiple products there.
Why did you choose kernel space and not just do like Fuse?
Can you repeat the question?
Yes, okay, sorry. Yeah, so why did we choose a kernel driver? So fundamentally, this is because we had the expertise. So we have a kernel developer, Zach Brown, who's really involved in the kernel file system community, and so he knows the kernel space. There's some limitations in Fuse that he found with being able to do the distributed consistency models that we required, and so there's some cache invalidation that was missing in the Fuse layers, and so we pretty much, because of the performance that we're looking for and the capabilities within the file system, it made sense for us. It's not for everybody. Like I don't recommend anybody just go try to work within kernel file systems, but for us we had the expertise, and so it made sense for us to work there. But being an in-kernel file system, we kind of get all of these services out of the box on Linux. So NFS, Samba, FTP, your direct CPs and rsyncs and everything, that all just works out of the box because those are just interacting with standard Linux VFS layers. But there's not an S3 connector out of the box in Linux, and so that's why we needed to focus on this project, is because we kind of had that missing component for the ingress and egress out of the systems for the clients that do require the S3 capability. So the way that the gateway works is that it pretty much just acts as like a protocol translator. We have pluggable backends, and so the S3 client sends your incoming requests into the gateway. The gateway parses the request and handles all the rules of like the S3 spec and stuff, validates the requests, checks the authorization and stuff. And then that translates the request programmatically into an easier to handle backend request. And so it looks like just calling a function with some arguments there that's a little bit easier to deal with for the backend developers, so that they don't have to worry about all of the S3 protocol specifics there. They're just handed, the backend system is just handed a simple struct with here's all the information that you'll need in order to complete this request. And then the backend result is handed back to the gateway, and that's encoded into the expected encoding, which is typically XML encoding for the client responses. Our current backends, we do have just a generic POSIX backend. It does require extended attribute support because we do have metadata that's stored in XAdders. But this is to enable kind of the general community out there. So we have our ScoutFS specific backend, but that's not going to be useful for everybody. So the POSIX one was really intended to just let the community be able to take hold and test this and play around with this and see what could be useful for more generic use cases out there. Also working with Los Alamos on the OCS devices and the other storage systems there. So we're open to collaboration on these backends. So it's kind of use the POSIX one or others that are a part of there when it works for you, but it's also extensible. So we're happy to collaborate on any new backends to new storage systems as well. Just to give an idea of like why would you want to do your own specific backend here. So we have a POSIX file system. So why do we need to do a ScoutFS backend? There's a couple of optimizations that we needed to do for ScoutFS. So there's the multi-part uploads basically come into the system, put in a temporary location for the part uploads, and then they're copied into the final object location in the complete multi-part upload call. This is just using the standard go io.copy that can take advantage of the copy file range if that's supported in the file system. But our file system has a slightly different ioctl for that called move blocks that allows us to move extents from one file into another without actually moving the data around. But because it is slightly different than the copy file range, it's a specific ioctl for our file system. And so now we have to have some special behavior in order to have that complete multi-part upload, not actually move data around within the system. That saves a full read-write copy cycle, so really improves the overall throughput of the system significantly. Another thing is the Glacier mode that we have. So we are a HSM system that tiers off to slow storage. Sometimes the request time for recall can be longer than what the S3 clients are willing to wait. So that you can get these S3 timeouts on the client side if it has to come back from tape, if you have to load the tape in the library and maybe wait for an available tape drive or something, that could be hours or days later on a really busy system. And so the Glacier model fits a little bit better with our system when the client is able to take advantage of it. So in our backend, you can enable or not the Glacier mode. So we do allow just kind of the default S3 access model where it is online, but then you can also flip into the Glacier mode where it'll return the appropriate errors for the offline file states and also trigger backend recalls for the restore object. I'll get into that a little bit later too. I'll go through the project layout. So this is what you see on GitHub if you visit the project, kind of divided up into these modules. This is organized by the features and responsibilities, so it's kind of a good tour to walk through the different modules that are within the system. First is the authentication module. So this does support multi-tenant. We do have the local accounts currently implemented through the POSIX backend. It's kind of limited. It's storing all the accounts in a flat file that has some kind of silly synchronization stuff across multiple gateways here, but this is meant so that you can have minimal dependencies. It kind of works out of the box, but the intent here is that we're going to expand this to have capability to interact with other authentication services. So we're probably likely to see integrations with like Keycloak and Okta and stuff in the near future. That would be more appropriate for kind of the enterprise sites wanting to deploy this for real in multi-tenant mode. And we're open to help with that if anybody has expertise in any specific authentication systems that they'd like to see here. The gateway has the notion of different roles within the system. And so you always have the root account. This is defined at runtime through flags or environment variables. When you actually invoke the gateway process, you have to specify what the root account is. And then that's never persistent. That's just defined whenever you run the gateway. You have this root account. So if you forget all your other passwords and everything, you can always just relaunch the gateway and you've got the root account right there. Persistently, we do store the admin and the user accounts. Admin functionally is basically the same access as the root account. And then the user account has more restrictions in there. So the admin's accounts are able to see all the buckets in the system, create new buckets, create new users, and assign the bucket ownership to the various users, where the users are only able to access their bucket that they've been assigned to. This is pretty common, so it's different from AWS. AWS is kind of a free-for-all. Everybody's allowed to create buckets, knowing the admins are the admins behind the curtains up there. This is more common for what you would see for on-prem object systems, is that you would want a little bit more control over the accounts and the buckets and stuff. We're thinking about maybe adding a user plus role or something that could also create buckets if you wanted some behavior that's a little more similar to AWS, but initially all of the deployments have wanted more control so that they assign the buckets. Especially on our system, we have policies that are path-based policies, and so they really want to constrain these users get these buckets so that we can say that the policy for this bucket is to create 2 tape copies always, and the other user only gets 1 tape copy or something. It's a little easier for them to apply the policies within our system. And this maps pretty well with like the expectations of kind of other on-prem systems, is to be able to manage those, the buckets and the accounts. The assigned bucket ownership is slightly awkward because that is kind of a bucket action, but that's part of our API because Amazon doesn't have a way to assign buckets to other accounts. So that's actually going through our admin API instead of the standard, because there is no S3 API for that. So I'll get to that in a bit, but we do have kind of a notion of two different sets of APIs here. We have the S3 API and our admin API. The storage backends, this is where most people, I think, would be interested when trying to deploy a new backend service. You'll be focused on creating your new backend within here. This is what houses all of the actual storage system interactions. So currently in there is the POSIX and ScoutFS modules. So to implement a new backend, looks something like this. You create your storage structure. If you embed this backend unsupported struct, that basically just returns the error not implemented for all of the methods, and so you can choose which ones you want to implement. So you don't have to implement the full spec. You can just, if you don't want to support multi-part uploads in your storage system, you can just not implement those, and it'll just return the error not implemented back to the client. And so this is kind of nice to be able to get started with it pretty easily, so you're not required to implement all of the interfaces for the first level of functionality. I've cut out all these, so the interface is actually a lot more functions than this, but it's kind of organized into the bucket operations, multi-part operations, the standard put, get object, list objects, and then we have some of these special case operations. So we take advantage of the restore object in our Glacier mode. Gary, I think, is going to be taking advantage of the query object content API. So we have a few of those kind of specialty ones in there. And then the tagging stuff. But you can see it's very much about the CRUD operations on the objects. So this is our Glacier mode. So we do simulate pretty much what the Glacier behavior is. So getting the object headers. So if the Glacier mode's not enabled, then it's going to just work like an S3 system, but the gets for offline objects might take a really long time, or it might time out. And so it may or may not work, just depending on like how busy the archive system is. So to have a better kind of user experience, as long as the application supports the Glacier mode, we can switch it over into the Glacier emulation mode, and retrieving the object headers will show the storage class as Glacier for the offline objects, so it gives the indication to the client of are these objects in cache and available or not. And also the transition state. And so this is what you would see in Glacier is it currently recalling the object, or is it transitioned to online, or is it just offline and staying offline right now? A get of an offline file returns invalid object state, just like Glacier would. So that doesn't need, that is the key right there, to not force a recall just for an accidental get to an offline object in the system. And so it has to be an intended recall, which is through the restore object API. So that'll trigger the backend recall in our system. We have some what we call stage notifications, and so the customer can get the notifications similar to what Glacier would when the object is online, or you can just keep pulling the headers to see is the storage class still Glacier, and is it still transitioning, or is it back online? I think the storage class is standard or whatever if once it's online. The command Versity Gateway is just the CLI command support. So this is where main is. This is where it builds the binary, it does all the flag parsing and everything. The integration tests. So we have kind of two sets of tests that will be running on our. Mostly this is just automatically run with the GitHub PRs, with the GitHub actions. But we have a set of integration tests here that is testing for like S3 interoperability. Thanks to the Ceph team for the S3 tests, we've really been working through those S3 tests. That has a lot more coverage than we have, but we've kind of looked at the failure cases, trying to decide which ones are important to us, and then we port those over to our tests to make it a little bit more self-contained, so that it's easier for us to just run through our full test stack here. We do also have unit tests, but those are more just covering the front-end API handlers. It's hard to do the unit testing for the storage systems because you typically need the storage system or some emulator running, and so that just makes it a little more complicated. So the integration tests are something that is just run with the CLI. You can just do the Versity Gateway test command, and that can invoke the client-side test. So you can run the test, you can run the storage server against your storage backend, whatever you need up and running, and then you can just fire off the test suite on the CLI to get the pass-fail criteria for all of the tests that are run. The S3 API directory is all of our front-end API handlers, and so this is where all of the S3 protocol processing happens. We are using the Go Fiber web framework in Go. This is kind of the state of the art when we polled the community for what frameworks are fast and supported. It's still under development. There's some other ones have been kind of deprecated over time. So the Go Fiber looked like the one that was kind of the most vibrant still in the community, still had good performance. A lot of people are still working on that one, so that seemed like the way to go for while we were starting this project up. It's worked really well for us so far. This processes all of the incoming requests and then translates it into those back-end API calls. This is both the S3 and the admin APIs are handled in here. You can run those as separate web service listeners within the gateway. So either they can listen on the same endpoint or you can separate those out. So there's some options where you can tell it, I want admin to listen on one interface and I want the S3 service to listen on a different interface. You don't necessarily have to expose the admin API to the world if you don't want to. The S3 errors is mainly just to encapsulate all of the AWS specifics. So they have both the HTTP status codes as well as like the long string of this is why this thing failed, and it's like kind of generic but then kind of specific, but we wanted to be as compatible with the clients as possible, and so we do encode all of these, the ones that we use, all of the error types that AWS would respond to, and so all of those errors are housed in the S3 error components here. And the way that it works is that the backends will return those error types back to the API service, or they'll return a non-S3 error type, which is just like a Go error type that's internal to that, and that would be treated as an internal server error. So that's assuming that like something went wrong with the storage system or interactions with that storage system. And so because it's an internal server error, the API server can see that that is an internal server error, and we can log that separately so that the admins of the system can kind of check that out and see what's going on with these, because these are kind of like unexpected errors within the system. We do have bucket event notifications as well. Right now this is meant more for like administrative or site purposes, so there's not a separate event per bucket. It is a global system, but we might be changing that if somebody's interested in doing per bucket events. But right now this is the same structure as AWS, and then it would apply to all the buckets in the system. We currently have integrations for Nats and Kafka, but it's also a modular kind of plug-in interface, so you can extend that to whatever event notification that you want. And we also have the server access logs that are also the same structure as AWS. So we're kind of see the theme here that we're trying to make it as easy for people to transition between this and AWS as possible. These can log just to a file, or they can be logging to webhooks. And if in the webhook mode, you can also do JSON encoded structures, so that it makes it a little bit more easier for like programmatically handling the webhooks. And then the S3 response handles all of the response, the S3 specific response formatting. So this is the S3 protocol wants like XML encoded responses and requests sometimes, and so this is the responsibility of all that deserialization and serialization is done in the types in the S3 response here. So that this is mainly so that the backends don't have to worry about this. So switching over to one of our customers that are using the gateway in production now is the POSI Supercomputing Center. They're a large radio astronomy site. we were able to transition their system over to our platform. And when doing so, they were also deploying a pretty large online Ceph data lake as well. And so they wanted to standardize all of their client interactions on the S3 protocol to interact with both Ceph and the archive. But they also needed it to be highly performant and highly available because this would be a kind of a critical service for them. So the way that their workflow works is that they do all their capture and compute from the telescopes onto the primary data lake. And then once they're happy with whatever they're doing to the data there, they want to save a snapshot off to archive. They will send that through the S3 connector across a cluster of Scout AM service nodes there. That's where we would apply the policy and make the tape archives for them. And then similarly, they need to often recall older data sets as well into the data lake. And so they would do something similar. I don't know that they're actually doing the Glacier mode, but they effectively do the same thing as the Glacier mode, where they pre-stage all of the, the known data sets that they need to recall into the file system cache. And then they would, in parallel, copy that back over to the data lake and get that ready for the next compute jobs. So this is all developed in the open on GitHub. All of the bugs and features are tracked in the GitHub issues. Full documentation that we have so far is all in the project wiki, so that's a really good place to start if you're looking for more information on both the user side and the developer side. We're trying to get all the information that we can into the wiki. All of the CI is done in GitHub Actions so that it's kind of easy to get the response on PRs for the pass-fail status there. We've enabled the GitHub discussions, but I'm not sure that that's the best path forward for communications. So if anybody has ideas of Discord or mailing lists or anything, if that would help collaborations, we're open to any ideas that would be the best way forward there. So yeah, please visit the GitHub repo and check it out. Thank you. Any questions or?
Are you seeing a lot of community collaboration?
So the question is, are we seeing any interest in collaborations across the community now? So surprisingly so. We've only been working on this for, I think, about 5 months now. And yeah, we get contacted pretty regularly from a bunch of storage vendors wanting to see, can we help with some support? You know, it usually is, can we include this in our product and can you support it? But we're much more interested, honestly, in people that want to contribute to the project to make it a little bit more community. So that's what I'm hoping to foster here is, developers that would be interested in collaborating. I think that's much more interesting for us because this isn't our primary revenue generator, so this isn't really the main product of the company. So I'm much more interested in like a developer collaborations than sales collaborations on this.
No one else, I will ask.
Yeah.
Do you have any kind of either Ansible or Terraform kind of,
Yeah.
extensively, not quickly
So
kind of thing?
The question is about provisioning. Do we have any kind of canned provisioning for the system? We don't. So the intent for this one is to be kind of very simple to run, and so it should be very easy to add to any provisioning, Ansible provisioning scripts that you want. We probably will be doing some like Docker containers and stuff to make it a little bit easier to deploy. But if you're interested in contributing any of that, we're interested to accept that.
I guess one final thing.
Sure, yeah.
Discord, just set up a Discord server.
Yeah.
I'm finding, I think a lot of projects now.
I think that sounds like the way to go.
Discord seems to be quite a good.
Yeah, so the comment was please do Discord. So yeah, I think we'll be happy to collaborate on Discord. That seems like that's the standard out there now. All right, thank you.